Hello everyone and welcome to part 4 of lecture 13 and 14. In part 3 of this lecture we talked about different mechanisms of heat transfer which are involved in the transfer of heat from flue gas to the process fluid, and we also looked at that how we can calculate the efficiency of the furnace. And I said that among other things the efficiency of the furnace also depends on the supply temperature or the flame temperature of the flue gas. And so today's lecture, we will talk about the flame temperature of the flue gas, and actually we will look at a concept that is called theoretical flame temperature. Okay, so when we perform a heat balance around a furnace, this heat balance can be used to determine the actual flame temperature, and the actual flame temperature is a function of the calorific value of the fuel, the construction and the type of the burner, the heat losses due to incomplete combustion or due to the loss to the ambient, or due to dissociation of the product or the flue gases. But in reality, we cannot quantify these factors beforehand because most of the time the design is iterative and we have to look at different parameters while we are designing to get the final flame temperature. So we use another kind of concept that is called theoretical flame temperature. Okay. So the theoretical flame temperature can be defined as the temperature that is attained when you burn a fuel in air or oxygen without the consideration of any loss or gain of heat to the system. Okay. And in reality, we want the actual flame temperature, but because as I said that it depends on a lot of design parameters like geometry, construction, and the type of burners. So we cannot get the actual flame temperature, and we start with the maximum flame temperature that we will achieve inside our furnace. And we design our furnace and then we recalculate our actual temperature based on the geometry of the system. Okay. And this theoretical flame temperature is also called adiabatic combustion temperature because, again, as I said, we are not considering any loss or gain of heat to the process or to the system, and that's why it is adiabatic conditions. Okay. So, in order to calculate the theoretical flame temperature, we need to account for all the energy or heat that is generated or consumed in the process of combustion. And you should have seen this from last year in process engineering fundamentals when you studied material and energy balance. So this is essentially the depiction of Hess's law, which states that the change in enthalpy in a reaction is independent of the path. What it means that enthalpy is a point function as opposed to a path function. Okay. So we start with a mixture of fuel and air, let's say at a given temperature T1, and then we burn the fuel and get the heat of combustion, and then finally we get to the point where we have the flue gas at a stack temperature. Okay. So that is reality, but in reality it is very difficult to calculate what is the heat of combustion or the overall heat of combustion. So to do that, we actually use a thermodynamic simplification to solve this system. So we again start at the same point. We have a mixture of fuel and air at a given temperature. We bring it to the standard conditions of 298 Kelvin or 25 degrees centigrade, and then we use the tabulated values of standard heat of combustion at the standard conditions, and then we have the flue gas, and then we change our flue gas from standard conditions back to the stack conditions. Okay, so instead of using this actual path, we are now using a standardized path, and the reason for using it because these values of standard heat of combustion are available in literature. Okay, and as I said, the Hess law says that this path enthalpy change should be equal to this path enthalpy change, so we always have the same value at the end. Okay, and so if we now do an energy balance, we can see that the overall heat of combustion should be equal to the heat that is carried by the fuel, and if the fuel is at standard conditions already, then this should be 0. But let's say the fuel is at a different temperature, so we have the enthalpy of the fuel. Similarly, we have the enthalpy of the air because of the different temperature between T1 and standard conditions. And then we have the standard heat of combustion that we, as I said, we can get it from literature. And then we have finally the heat that is carried by the flue gas going from standard conditions to the actual stack conditions. Okay. And because we assume that it's a adiabatic combustion, because we are calculating adiabatic flame temperature, so here we can assume that no heat is lost. So all the heat is accounted for. The heat of combustion is going from the fuel to the flue gas. Okay. So delta overall heat of combustion is 0, and then we can rearrange the equation to get the enthalpy change of the flue gas. And these enthalpy terms can be calculated by the equations given here. So you have delta H of fuel that should be equal to integral sign going from T1 to standard conditions Cp times delta T. Okay, so similarly you can do it for the air, and then for the flue gas going from the standard conditions to the actual condition. Okay, and here you have the definition of different terms. So here you have the 3 heat capacities involved in the system, and if you look at it, that these are the molar heat capacities, and that's why you have the unit joule per kilomole per Kelvin. Okay, and here I'm just providing you some of the standard heats of combustion for typical fuels. For example, we have carbon or sulfur, or we have natural gas that is, as I said, is the most common fuel, and other ethane and propane. So if you look here, that we are given the standard heat of combustion at 290 degree Kelvin in megajoule per kilomole of fuel. So it means that if you burn 1 kilomole of methane, it will release 802 megajoule of heat. Okay, and these standard heat of combustions can be found in different databases like Paris Handbook, or different softwares like Aspen and Hysys. So another thing to remember is that Cp here is a function of temperature. You should know this from thermodynamics, that Cp changes with temperature. And because we have such a huge change in temperature going from, let's say, 25 degrees centigrade up to 2000 degrees centigrade, so we need to account for the change in Cp with temperature. Okay, so there are 2 ways we can do that. So we can estimate the Cp value either using a polynomial expression that is given here, where Cp is a function of temperature with some constants alpha 0, alpha 1, alpha 2, alpha 3, and the value of these alphas can be you can get it from, for example, Paris Handbook, or from some software. You can calculate the effect of temperature on the Cp. Similarly, you can use a mean value approach, where you are looking at the molar mean, where you are simply taking the integral of Cp times delta T, changing from temperature T1 to T2, and then you are dividing it with the difference between the temperature. So this is a molar mean of the Cp, and that helps you account for the significant change of Cp with temperature. And here again, I am just providing some of the mean values of Cp at standard conditions, going from 25 degrees centigrade to T, that is the temperature of your system. And here you can see that here you have the temperature values changing from 25 to almost 2000 to 2200 degrees centigrade. And then you have Cp values for some of the most common gases present in the flue gas. So here you have oxygen, nitrogen, sulfur dioxide, and a range of natural hydrocarbons. Okay, and if you look at the value for oxygen, so you can see that at 25 degrees centigrade the value is around 29.41, but as the temperature changes, let's say around 2200 degrees centigrade, you can see that the mean Cp value changes to almost 35.62 degrees centigrade, and that is quite a big change for the Cp. Okay, so that is why it is important to take into account the change of Cp with temperature. So that is all for this part. In next part of this lecture, we will look at an example and practice some of the concepts that we learned in previous parts of this lecture, and then see how we can calculate the theoretical flame temperature. Okay, thank you for your time.